A very warm welcome on behalf of JCRC Foundation. It's my extreme pleasure to announce that Department of Mathematics first year is blessed with your gracious presence on the occasion of International Mathematics Day, which we together are celebrating in the form of this international symposium. JCRC Foundation is one of the most distinguished institutes in Northern India with educational legacy of 23 years. It is derived by culture of excellence, research, and innovation. In our today's symposium, we have 4 speakers from around the world who want to share the excitement and joy in mathematics. Now, I would like to request Dr. Ruchi Mathur ma'am to welcome the very first speaker of our today's symposium, Professor Brian Winkle, sir.
Thank you, Sumedha. Am I audible?
Yes, ma'am.
Thank you. Welcome, sir. Welcome, Professor Brian Winkle. A very good morning, sir. Good morning from India. It's my honor to now introduce the very first speaker of today's event, Professor Brian John Winkle. Let me introduce Professor Brian Winkle to you all. Sir is founder and director of Symbiote Systematic Initiative for Modeling Investigations and Opportunities with Differential Equations at Indiana University, Bloomington, Cornwall, New York, United States.
I'm sorry, Ruchi, but I can't hear you. Can you hear me? Can anyone
yes,
hear
sir,
me?
you are audible. Yes, sir, you are audible.
Meda,
I can hear
you hear me?
We can hear you, sir. Sumedha, please see if there is some technical error. Why sir is unable to hear us?
Yes, ma'am.
Wait me. अरे बोली
Hello. Sir, now
Hello,
can
sir.
you hear me?
Can you hear us? Hello.
सर स्टूडेंट्स को भी नहीं सुन पा रहे.
Ma'am, can we ask him to rejoin again?
I can't hear anyone, but you can hear me. So if you will tell me when to start by waving, then I will start. Sorry, I can't hear.
Sir, you are audible.
I think we have to ask sir to rejoin the meeting. There is technical issue from sir side.
नाम
Hello. Can people hear me now?
Yes, sir, we can hear you now.
Okay. I apologize. I had to switch computers. So,
No, sir, no issues. Sir.
am
Sir,
I
am
ready?
I audible now?
Yes. Am I ready to begin talk, or should I wait longer?
No, you may begin, sir.
Okay. Thank you very much. And I want to share my
Only
screen.
waiting for your address, sir.
Oh, okay. And just a moment. Now that I had to switch computer, I have to get the talk that I'm going to give. And excuse me a second here. Okay. Excuse me, I can't. Okay. I want to share my screen and then I can get going here. I'm having trouble sharing my screen here. When I click on the share screen button, I can't. Oh, I'm sorry. Maybe now. Okay.
Yes, sir. Now we can see your
Okay,
screen.
I apologize. I have to make this bigger, but yes. Okay. All right. So I'm happy to be here, even though I'm electronically having difficulty. I am pleased to be talking to both students and faculty. And what we're going to be doing is talking about some experiences with mathematical modeling and differential equations from real life. And as your introduction said, I am the director of Symposium, which is a project to help teachers and students using modeling to teach differential equations. I'm very happy to be at your school, even though I am in the middle of the United States in a part of the country which has 3 centimeters of snow falling right now. And it is a pleasure to be in your warmer climate. So that's a picture of me in London in the catacombs having a meal several years ago. And this is your lovely campus. And I'm pleased that I was able to find a picture of your faculty and students who look happy. Just some personal items, because I think it's always worth knowing something about who is talking to you. I was an undergraduate from 1960 to 1964. That gives you some idea as to how old I am. I was headed for a ministry. I was going to be a Lutheran minister. That's a denomination in Christianity called the Protestant faith. And but somehow I got more interested in mathematics than theology. And I pursued mathematics as an undergraduate major. I was a tutor. I worked in the math club. I became the president. But all the while during college, I was the chapel organist. So I maintained my connection with my beliefs. And but I also worked in food service and so forth. I got a PhD from Indiana University, which is in the state of Indiana, in 1971 on a very theoretical mathematics in abstract algebra called ring theory. But when I moved to my first teaching position in a small liberal arts college in Albion, Michigan, the state of Michigan, I found the science library and I began to read about applications of mathematics that I had never known before because I was so focused on my PhD in abstract mathematics. And it was from the first year of teaching in 1971 that I basically turned my life towards applied mathematics. I only taught an abstract algebra course once in 50 years, even though I had a PhD in that. And so what I'm trying to tell you is your life can change drastically in many, many ways, and you have to let things pull you and draw you to those things which are attractive to you. Mathematics was attracting to me over theology, and applied math was more attractive to me than pure math. I had a chance to work for the summers for the United States National Security Agency. They're the ones who try to read other people's emails and make up secure message communications and cyber stuff. And I got fascinated with cryptology. So in 1977, I and 3 other colleagues formed a journal, which is about to be 50 years old pretty soon. And it is a standard journal on cryptology, history, political science, mathematics, computer science, code breaking, etc. In 1990, I founded another journal on undergraduate research, undergraduate teaching. And that one is not as old, and both of them are now edited by younger faculty. I turned it over to them. The reason I point that out is I never started out being an editor of a journal. I never thought about doing that. And all of a sudden, I was the editor of 2 journals, actually a third one on microcomputers. And that never occurred to me as part of my career plan. So look for opportunities, and sometimes opportunities will look for you. Okay. And in 2013, I founded Symiode, which is the systemic initiative for modeling investigations and opportunities with differential equations. I retired from full-time teaching as an emeritus in 2012. So what I'm going to talk to you today about is 4 examples of models that are kind of interesting. One is a gas model for the gas that they inject in your eye after an operation. And this is a personal one because they did that to me. Another one is the LSD drug model, and I had nothing to do with LSD drug. And another one is a model of a falling column of water. And then finally, for engineers, what's called tune mass dampings that keeps structures from swaying in the case of earthquakes or wind shear. Just to point out to you that all of the materials that I'm going to be talking about technically are available at Symiode. And if you go to Google and just type Symiode cubes, you will get to all of this material and you will see lots and lots more, hundreds of lessons and opportunities to see differential equations in applications. So I want to talk about these specific examples. I do want to mention that we have 3 other features inside Symiode. One is Scutum, and if you go there, you can see, and this is an international competition or challenge where teams of 3 students work on problems, and all of the problems for the past 7 years are online. You can look at them, and videos of the past few years for the outstanding teams. We have hundreds of students from around the world participate, and the videos of the 20 plus outstanding teams are on our YouTube channel. And once you go to the Symiode Cube site, Cubes is the host for our Symiode community. once you go there, you can get all of this stuff. Expo is a conference we hold in February, and we have a low price textbook for $39 for a electronic version that's modeling based. So it's talking about teaching differential equations and the mathematics of differential equations by using modeling up front and first. All right, let's go on and begin to look at some of these models. When you have an eye surgery, one of the things that you do is the doctor performs whatever. Of course, he may put you to sleep or just a local anesthesia, but he will essentially, or she will do something. And in my case, I had a torn retina. And what they do is they drain the fluid from the retinal region. There's about a 1-inch diameter eyeball is what we have. They take that fluid out. They perform the surgery all with robotic or micro instruments through your eye, including a TV camera that's right into your eye so they can see exactly what they're doing. And sometimes in surgery, they don't put you totally asleep. So one time I had a surgeon and I could watch what they were doing in the TV monitor above my head and without feeling any pain. So they put this gas in. It's an inert gas, argon or something like that. And essentially the gas is there to be a pressure on the wound and keep it dry so that the wound will heal. And they want to know how the gas is essentially absorbed into the body and the fluid starts to come back. And the reason they want to know that is that if you go on an airplane and you have gas in your eye and the airplane pressure drops, the pressure in your eye is from ground level. And my doctor told me you will feel very uncomfortable from the internal pressure. Okay. And I later read in the literature that it isn't just uncomfortable, but your eye could explode. So I told my doctor that I read about eye exploding, and he goes, that is not a very good term to use with patients. So he just told me it would be uncomfortable. Can you all hear me okay? Yes? Yes?
Yes, sir, we can hear you.
Okay. All right. But how does the gas get out and how is it replaced by bodily fluids? So here's the eye, and basically the bubble of the gas is at the top and the fluid is at the bottom because the fluid sinks there. But when you look at it through your eye, it's inverted. Eyes are inverted. So your liquid looks like it's up top, but the gas bubble is down there. And you know, when you go to an eye doctor, they dilate your eyes and then they shine a light in and they look and see. Well, what the doctor is looking to see is how much the gas bubble has dissipated or gone back and how much fluid has been. Because if there's still a lot of air, then you cannot travel by airplane. And at this time I was going to a job interview, and instead of flying, I had to drive a car to make the job interview because the gas was still in my eye. This is some data, and it's more than you want to know, but this is a given patient. This tells you the kind of gas, and this is the number of days after day 1, 2, 3, 4, 6, 13, so forth. This is information on that the ophthalmologist measured on how much gas there was left. And the volume, they measure the height to the menisca. In other words, they measure this height and they can compute the volume using formulas, but we could do that with calculus, the volume of a hemisphere or something. So this one has perfluoropropane gas, and doctors use different kinds of gases for different reasons, some just professional preferences. So the question is, how do you get rid of the gas and get the fluid? And one model is that the rate at which the gas bubble changes is negative and proportional to the volume. So if V is the volume of the gas that's in your eye, then as time goes on, it decreases because liquid is filling up and the gas is dissipating through the membrane. and it decreases at a rate proportional to velocity. Now, many of us would say that sounds pretty good. The more gas that's in your eye, the more the more per unit time is going to go out. Except the way that the gas escapes is not proportional to velocity. It's probably proportional to something else. And that something else, if I was teaching a class, I would wait and ask for students to volunteer. But that something else is the surface area. So how much surface area there has, that will tell you more than how much volume there is. And of course, here's one formula that says the rate at which the volume changes is proportional negatively to the surface area. Most often in science and chemistry and life sciences, rate constants are positive. Quite often they have units 1 over time. This K doesn't have units 1 over time because we're changing velocity with respect to time, and we have surface area here. So one way to get the units the same, I take the surface area and raise it to the 3/2 power. If you take the square root of centimeters squared, you get centimeters, and then you cube it, you get centimeters cubed. So this would be a formulation of a model right here. dV dt is minus K S to the 3/2. But I want to go back to the diagram and point out that not only does gas escape through the membrane, but it can escape through this meniscus into the fluid in the eye. A little bit can go and diffuse into the fluid. Most of us know that that's probably not that much, because if we open a soda pop can, very little of the gas goes back into the liquid. It tends to come up through the glass top. So here's another volume formula. It says the rate at which the volume changes is proportional to the surface area and the surface area of the menisca. So you're losing gas 2 different ways, and there are 2 different rate constants. You have initial conditions for all of these, and back to the original model that doctors use. So in Symio, there's a modeling scenario on this that leads students through all of these and asks them questions and gives them data so that they can check on different patients. All of the data is anonymous. I got it from ophthalmologists in Connecticut, hundreds and hundreds of patient data, so you can try it out, the model on many. And while these models are perhaps more true, it turns out that the rate at which it's proportional, the rate at which it decreases is proportional to the volume is pretty good. And it's an exponential decay. And of course, that means we have a notion of half-life. And that's what the medical profession, the ophthalmologists, used. These models are more accurate, but this model is quite accurate enough to within 1 or 2% over the time of the gas bubble, which is usually about a month. And so the doctors know that when they give this gas, they know its rate constant, and they know that it will last for 3 weeks. This gas will last for 5 weeks, et cetera. Okay, so this is the model they tend to use. It's a simple exponential. It's a simple exponential decay, and it's good enough for the medical profession. It's very good, in fact. Okay. So I want to go on now to talk about another application. This came about in the 1960s when they were studying the effects of drugs, and this was LSD, which is a hallucinogenic or euphoria drug that, of course, people were taking for recreation to get high, and it's illegal to use it. Even though marijuana in the United States is becoming legal, LSD is still not a legally purchasable drug. But they asked for college volunteers at a university, and 5 male volunteers stepped up and said yes. And what they did is they injected the drug into their arm, and they monitored the concentration in their arm. That's called the plasma. It's in the bloodstream, and they could monitor that by sampling every 1/4 quarter of an hour, half an hour, 1 hour, 2 hours, 4 hours, 8 hours. And here's what the plasma concentrations were. By the way, they also gave them a math test. And as they got more and more under the influence of the drug, their scores went down. These were simple arithmetic tests. Okay. So what they wanted to do is they don't want to know what the drug is doing in the plasma because they can sample that. What they do want to know is where is the blood when it's not in the plasma? And the answer is it's in the tissues. It's in the organs. In this case, it's in the brain. This drug affects brain function. Other drugs you might want, like iodine-based drugs, would be good for a thyroid condition. Or maybe you have a cancer and you have a chemotherapy and you want the drug to concentrate in a certain organ, and some drugs are good for one organ and for another. So this whole modeling is called pharmacokinetics, and it's massively used by the drug industry to determine the effectiveness of drugs. And when the doctor tells you take one of these pills every 4 hours, why she's telling you that is because they know that it peaks and then the amount of drug goes down and then you need to re-up and get more. But you don't want to take too many or else you will overdose. So this is a simple 2-compartment model. You have the concentration in the tissues, C sub T, and you have the concentration in the plasma. M is the mass of the body. These were average males at about maybe 70 kilograms. And then you have the concentration in the plasma. So about 10% of the body's mass is tissue and about 16% is plasma. The rest is bones and things like that, okay? So what happens is you inject it into the plasma. It begins right away as the blood goes around, it begins to go across membranes into the tissue. And in medicine, you want that. You want it to go into a tissue and to kill the germs or the cancer. In the drug case, you want it to go into the brain so you can feel euphoria, etc., or you don't feel any pain. But it also diffuses back from the tissue to the bloodstream. Remember, the blood's circulating and feeding the tissues all the time. So across that membrane, you can get blood, drugs going in and drugs going out. And then, of course, some drugs are eventually excreted through urine or sweat, or just they're broken down. They're metabolized by the body. So here you have a little discussion, but the bottom line is what we have is 2 differential equations. We have the volume of the plasma times the rate at which the concentration changes. So the units here would be cubic centimeters, and then this would be the concentration would be per milliliter, how many milligrams or nanograms of the drug per milliliter per unit time. And what you have is some of it comes in and some of it goes out. Remember, we go back to a model like this, some is going in and some is going out. So when you put these together and you keep all of your units straight, and one of the things I stress to my students is units, 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 all the time, check units. You don't want to be adding apples and oranges. You don't want to be adding amperes with molecules. You want to be sure these units are all correct. And many times the constants can absorb units, but in general, you want these constants to have just units 1 over time. They're called rate constants in the field of pharmacokinetics or kinetics in general. So what you get is a system of 2 linear differential equations. And remember now, we have data. We have data on the patients. What don't we have? Well, we don't know these rate constants. And by the way, the pharmacy companies want to know the rate constants. They want to know how fast that drug will absorb into the body. And they want to know how fast the body uses it. And by the way, if you're taking a pill, you'll notice some pills have coatings and they're big. When it goes into your stomach, they want sometimes it to take a little while before it becomes absorbed into the bloodstream. So in your stomach acids will eat away at the pill until finally it's all absorbed into your bloodstream. This is in the vein, it's called a plug, and it's just one shot. A bolus is what it's called. So in this case, we're not taking the drug through a pill. We're not putting it on our tongue, which is the popular way that drug users do it. We're just taking it through an injection in the vein. So we have these parameters, Ka, Kb, and Ke, and we want to know these parameters given the data. So this is a system of differential equations, and if I solve this in Mathematica, it would fill up 2 pages. It is huge, it is messy, it has constants in it, but it is closed form. This is a linear system, so you can actually get an analytic closed form solution, and it has lots of parameters floating around in it. And the formula that would go right in this box in the summation, that's called the concentration in the plasma at time Ti, where I is the first, second, third, up to the 7th observation. So this is the amount observed, and this is what the model predicts. These terms C sub P are messy, massively messy, and we're having 7 of them, and we're squaring them, and we're adding them up, and the only unknowns are these parameters. K sub A, K sub B, K sub B. And the pharmacy companies want to know those parameters to determine how fast this drug is being absorbed and how fast it's being used and how fast it's being expelled by the body. And so we go into Mathematica and we give it a powerful command. We say, look, take the sum of the square errors between the model and the observed. It's a very common approach. Square that, and now find the parameters which minimize that. We can do that in one fell swoop, in one command inside Mathematica or Maple or specialized pharmacokinetic software. And what we get is the parameters Ka. These all have units 1 over time. Here's what they all are. The sum of the squares, that is the difference between the observed and the model, is less than 0.08, which is very good, and I'll show you in a plot. And this is the amount of concentration in the plasma that the model predicts. And so one of the things you want to do is look at how good your model is compared to the data. The best way to do that is to look at a picture. So here's what the plasma concentration is on this solid line according to the model. And these boxes are the actual data. So when my students actually work with this model, it's very powerful, this image, to show them how good it is at predicting exactly what you can measure, namely the plasma concentrations for LSD, and the same true for other drugs. So here's what we will gain. If we then take those same parameters and put them into the tissue concentration, this is what our model predicts, namely the concentration of LSD in the tissues, and indeed in the brain, it rises rapidly. Within the first half hour, you have maximum amount of LSD in the tissues. And if you're taking this drug for illicit purposes, to get high or to get euphoria, this is what you want. If you're taking it to kill cancers, you want it to get there and do its business. And after a while, it will dissipate. And what do you do after 4 hours? You give another dose, another pill or something like that, and then you will build another spike. Okay? So as a coincidence, this is the performance on the math test versus the tissue concentration. So one of the things you can see is as time goes on, as the concentration goes on in nanograms per milliliters, the performance on the exam goes down, which is what you would expect. If you're under the influence of a psychedelic drug, you probably don't function very well during arithmetic. And that's just an afterthought in the experiment. Okay, so now I want to talk about something quite different. This is a physical model, and the kinds of people that are interested in motions of water and fluid are chemical engineers in particular, and civil engineers who are dealing with sewage and water flow treatments and conduits and how things build up. They don't want pressure to build up in water pipes. So they're always interested in just simple models so they can explain to their students how things go. So if you go to, again, Symbiote, and there's a YouTube channel. So if you just go to Symbiote on YouTube, you'll see a video. And this video has a clock, and it has a 2-liter bottle of water, and it has a food dye in it. And as the clock goes on, the water falls by going out this spigot. Okay. So what we want to do is model the column of falling water. And the students can go online and collect real-time data. And when they get that data, then they can do their modeling. So let's together do this modeling. They can, as I just said, they can see, they can conjecture an empirical model, namely fit some function. They can build an analytic model, which is what we want to do most importantly. They can create a differential equation from that. They can solve it, they can estimate the parameter, and they can finish the modeling activity by comparing their model to actual data. So here's what we have. Remember, what we're monitoring is the height of this column of water as time goes on and the water just falls out. Clearly, most of you would say that initially the water is going to fall more rapidly because there's a lot of pressure. And later on, it's going to fall more slowly. And one of the things you can see is right here is the plot of the data in seconds for one of these columns of water. It was at time 0, it was 11.1 centimeters, and it dropped to 10.6. And you can stop and start the clock anywhere you want. That's why these times are the way they are. And one of the things you can see is the data, the height is falling, but it's not quite linear. In fact, it's slowing up a little bit, not much. So one thing students might try to do is they might try to put a straight line through it. So here's the data, and you're in Excel, and there's a trend line in Excel, and you can put a data line through, and that's not reassuring because first of all, good models have residual errors that are random. So you should have a little bit high, a little bit low. This is too systematic. It's a bow shape, and we're looking at a straight line. So here's another bow shape, exponential decay. This is the best exponential decay function, and it really doesn't do a good job. Okay, something better has to happen. So we could spend all day long. You could put a 20th degree polynomial that go right through that, but that's not going to give you any sort of physical intuition. So one of the things we try to do in our classes is try to give an equation that says, at what rate is the height changing? dH/dt. This is usually in a differential equation course. So obviously we expect to use differential equation models. And from the data, we can take some notions and we can say in the first time interval, it falls at a rate of around 0.22 centimeters per second. But then later on, it only falls at the rate of around 0.12 centimeters per second. So it's falling at a slower and slower and slower rate. Okay. So here again is a picture, and you can see that it's falling at a slower rate at the right-hand side. And now we come into Evangelista Torricelli. He was a student of Galileo. He invented, in Western Europe culture, he invented the barometer, which tells you about air pressure. And I really like this painting because it shows he has a wicked, wicked mustache. So Botticelli's law that he was able to establish, I'm telling you it right up front, but in a moment we'll go through a derivation to show you how we might do this with students. What it says is the rate at which the height changes depends upon the height. And in fact, we had this feeling before that the bigger the height is, the bigger the rate at which it falls. So dH/dt is proportional to height to some power. We don't know what power it is, but Torricelli says it's proportional to the square root of height. And we'll show why that's true here in a moment. G is the gravitational constant for wherever you are on the Earth. If you were to do this experiment on Jupiter, you would have a huge G. If you were to do it on the moon, it would be much less. B is some parameter that might be the viscosity of the fluid. It might be the aperture of the hole. It might be the friction of the hole. Many, many, many different things. And engineers are interested in that parameter and breaking apart what it really means, in particular friction at a hole. A civil engineer does not want a lot of friction when the water is exiting one compartment into another. So what we're going to use is the law of conservation of energy. Now, when you're teaching differential equations, sometimes students haven't had physics and they get very nervous because they're thinking, I don't understand this, I don't know this, but what I'm about to show you is a kind of an explanation. Most mass has energy. It has electrical energy, it has chemical energy, it has atomic energy. It also has another kind of energy called kinetic energy, that is, it's moving, and it has potential energy due to gravity. If you let it go, it will fall. If it's less high, it has less potential. And these energies can be measured, and some are of interest to us and some are not. We're not interested in atomic energy in the molecules. What we're interested in is the mass of the slab of water at the top and how it falls to the bottom. And the conservation of energy says that if you have a slab of water at the top, the kinetic energy plus the potential energy is exactly the same as when it's at the bottom. So one of the things you use in science and engineering is you compute something in two different ways and you set them equal and you get an equation. In our case, a differential equation. So here I have to just tell students the kinetic energy of an object of mass m and velocity v is 1/2 mv squared. I don't spend any time deriving that. I also give them a plausibility that says if it's traveling at a v is big, then there's a lot of kinetic energy. Think of an accident in which a Mercedes-Benz hits a car. It has a big mass and a big velocity, has a lot of kinetic energy. Another one would be a motorcycle, has a lower mass, might not be traveling as fast. Then this is the potential energy. It has to do with the mass, gravity, and how high from a given fixed point it has. So we have this slab of water that has some initial velocity, so it's kinetic plus potential. And then finally, when it gets down to the bottom where the hole is and it's about to exit, it has a final velocity and it has a height of 0. So this is mg, the height of 0. This is the final. If we set these two equal to each other, and we note that that this is 0, what we can solve is the final velocity is the square root of 2gh plus the initial velocity squared. And if we just start the process and we open up the hole at the bottom, the initial velocity is 0, so we can get rid of this term. So it says that the final velocity at a height h of a falling body of water is just square root of 2gh. And so if we want to find out how much volume is being lost, we need to multiply that by some constant which reflects the size of the hole it's going out of, reflects the diameter of the cylinder, the viscosity, the frictions, et cetera, et cetera. Okay, so the square root of 2gh back in this formula, that square root formula, that's where that comes from. It comes from the conservation of energy principle. And now we're back to the general formula, okay? So when I teach differential equations, I haven't taught my students how to solve this kind of differential equation until they see this. I haven't taught them separation of variables. They now want to know, how can we determine H? So I then say, let's talk about a strategy for solving it. So I'm motivating the solution of the differential equation by a physical model in which they have collected the data. And they're going to try now to solve this differential equation. So I introduce the separation of variables. We divide both sides, we separate the variables, we integrate both sides. You use many different notations, I understand. I'm using a convention here. We introduced C, the constant of integration. We follow through with our analysis to finally get H of T is equal to, and by the way, en route, we can find out what that constant of integration is. And so here we have a formula. It says the height is something squared minus B, the square root of G over 2T plus some constant. And if I put the numbers that I know, namely the original height is 11.1 centimeters, and the gravitational constant where I did this is 980 centimeters per second squared. If you do them in different regions, north of you in the Himalayas, then your gravity is going to be much less, not much, but less. So putting the numbers in, here's what we get for a final model. We know everything except this parameter B, okay? We want to determine this parameter B. So how might we do that? Well, we go back to the sum of the squares. This is a messy formula and it has B in it. This is a number from our observations. We have 9 observations. We take the sum of these squares in terms of the parameter B, and we find out what's the minimum value. We could do that in Maple, Mathematica, Sage, lots of tools, but I've done it in Excel. And if you've not used Excel solver command, it's worth looking up Torricelli's law and the materials that accompany this inside Symbiote. What Torricelli's law says is that we think this is the model over here. I know that's small, but that's the analytic model. We don't know a parameter. We'll just put in a guess. And one of the things you can see is that the model is a little high. The data is down here. So we could tweak and change B, maybe make it 0.003 and see if we can get better fit. But what Excel has is the ability to do a solver. And what solver says is, I want you to find me the best parameter B that minimizes the sum of the square errors. And when you do this for the first time, it's like magic. And if you look at the materials that I put up on Symbiote, you will see that. And the best fitting parameter, here's the plot of the data over the model. And when the first time I ever used Excel solver, a student showed me this maybe 20 years ago, I thought I did something wrong because I only have one plot. Well, it turns out there are 2 plots. One is in red, that's the model, and one is in blue. But the model is so good at predicting it, they're right on top of each other. Remember, this is a physical model. This is not human nature. It's not biological growth mechanisms. Your model should be very good at predicting a physical model, and indeed it is. So we're estimating the parameter in the falling column of water using Excel. Finally, then, let's talk about a tune mass damper. I was teaching a differential equation course for engineers, and I got to teach with a colleague who was a civil engineer, and he talked about tune mass dampers. And these are large structures. Think of M1 as a tall, tall building in a city, in the city of New York, which is where I used to live nearby. These structures, these can be 80, 90, 100 stories high. And what you do is you put a large mass structure, which swings back and forth, and I'll show you a picture, so that when the building itself begins to sway, either because wind is blowing across it or because an earthquake is shaking it on the bottom, the mass up top counters it. And so what you get is a dampening of the motion so that the building will not tumble. Here's one in Taipei. This is perhaps one of the most famous ones of all. This is just the top of the building. And what this is an 80-ton steel ball on a pendulum that's in the middle of the building. So as the earthquake is moving the structure, the ball is countering that and causing it to not sway as much. There's a restaurant on that floor, and you can eat your meal while watching the ball sway back and forth. I don't think I'd want to do that. I would be very uncomfortable watching that ball. But these are other such structures. Here's one that's in San Francisco in the United States, and they put a large water tower on top. So when the building starts to sway, the water moves back and forth. And when the building is swaying one way, the water is moving the other to pull it back. And it has the added feature that if there's a fire in the building, they can just release the water and it can go down to whatever floor they need to put the fire out. These are structures that are usually found below bridges that you and I don't see to keep buildings from swaying or bridges from swaying. This is a structure that's often put on wires from electricity. And this is an example of what a structure might look like on the top of an office building. This is a giant structure, maybe 20 kilometers by 20 meters by 20 meters. So it's massive. And many buildings are retrofit. So this is the differential equation. If you think of all we're going to do is monitoring the displacement, horizontal displacement of a building. And we're going to hit it with an earthquake or a wind velocity that's blowing across it, much like a flute instrument. It makes vibrations. So here's what we have. We have a mass of the building. We have some resistance, and that's called a stiffness. And we have a resilience of the building to restore itself. And then we have a velocity, a sinusoidal motion that's going across it like an earthquake. And it has a frequency. Earthquakes have maybe 8 hertz frequencies. What this is a map of is this is a map of the amplitude, the maximum amplitude that this structure we're modeling will reach, depending upon the stiffness, depending upon C. So as you change C for a given input frequency, you get 2 things. Obviously, this building has less resistance, so it's going to sway a lot more. This building has a little more resistance, and this one has a little more. And that resistance comes from steel structures and the way that the architects and engineers build the structure. So you get these kinds of curves that engineers are interested in, and they also are interested in what will this response curve look like if we change the frequency. So if we want to build a building which will minimize swaying due to wind and minimize swaying due to earthquake, we're going to have to, accommodate both of these. And you might not think it's much, but if you are on the 80th floor of a large skyscraper and it's very windy, your coffee in your cup will start to slosh back and forth. And that can be very, very upsetting to people. Plus, they will look at the skyline and it'll be moving. So you don't want that to happen. And that's what goes on. So what this is a simple schematic for the building mass. And this one has no resistance. It just have a spring constant or stiffness. And this is the tune mass damper mass. And what we can do is we can put a damper in it, or we can not put a damper. And what you get is structures like this. This is vertically representing the same thing. And this has a spring constant, and it has a damper, and it has a vibration, and it has 2 displacements. And so you can build a system of differential equations by using these phenomena, and you can get you can see how well your damper works. And one of the things, if you go back to this building, you don't want to use half of the building just for your damper. You want to rent apartments, you want to rent office space, so you don't want to fill up the top with just a damper. So you want to do this responsibly and cheaply, but also safely. These buildings with tune mass dampers did not exist before 1965. And it was put into a Citicorp banking building in New York City, retrofitted after the building was built because the building was swaying uncomfortably and they needed something to mitigate that swaying. So many, many structures now have these, including small structures. Every hospital has them in operating tables. Think of an eye surgeon and you're sitting there above a subway train station under the hospital. As the train comes rumbling through, the whole hospital kind of vibrates a little bit and the operating table vibrates, and the eye surgeon who's operating on your eye your eye is vibrating in front of her. So what you want to do is dampen the surgical table. So you put these 2 mass dampers under surgical tables. So they're all over the place. You just don't see them, but they're powerful in their effect. Okay, I'm going to close up with just a few more things and tell you that Symiode has many, many, many project ideas and resources. If you go there, you can see them. You can download them. We have the student versions, which have the questions. And if you register as a teacher, and everything is free there, you can get the teacher version, which not only just doesn't just have answers, that's not issue, but it talks about how is the best way to teach that. Each author discusses how they use the material in class, how much time it takes, what could be a stumbling block, and so forth. You can go searching by keywords. So here's one modeling on guerrilla warfare. Here's one on half-life. Here's one on herd immunity. And here's one on heat and gravity and growth and glucose tolerance and so forth. And each one is referred to, if it's a article, it's referred to here. If it's a scenario that's complete, then it's referred to there. So one of the things I tried to do in teaching is always try to find out what the students were taking as cognate courses and relate the mathematics that I was teaching them in differential equations to that course. So if they're in chemistry, I was talking about kinetics. In fact, I'd have them bring their chemistry book to class and we would get data from their chemistry book. If it was in life science, I would talk about growing bacteria or protozoa. In economics, you'd talk about a phenomena like increasing interest rates. In sociology, group interactions. In linguistics, the immersion of new words in a literature, the transition and the absorption of words. So get their textbooks. I'm talking to the teachers now. Here's one. This is a Symiode modeling scenario that I wrote years ago, and it talks about chemical kinetics. And it's data right from a straight chemistry textbook. Here's the data. It's hydrogen peroxide. It's the stuff you put onto a cut to disinfect your cut. And it breaks down into water and oxygen. If you leave it in the container, eventually it has no power because it's just water and oxygen. So here's some data on hydrogen peroxide, and we have the students build a differential equation model and estimate. Here's one on modeling evictions. If the economy changes, the number of people who get evicted changes. If they take more risky behavior and they have to default, they get evicted. Here's the word jumbo. So in the 19th century, an Indian elephant was brought to the United States by an entrepreneur named P.T. Barnum. He was a circus man, and he gave the elephant the name Jumbo. No one had ever heard in the United States or in the English language the word jumbo. And if you go to Google, you can track the use of the word jumbo in the English-speaking literature from 1880 up until the current day. And now in the United States, you go to stores and they have a jumbo drink and you have a jumbotronic screen. And so everybody knows what jumbo means, but it all started because of an elephant from India. And so you can have your students figure out what the rate at which the word jumbo appears in the language changes over time. Set them free to find their own projects. I give you a warning, fitting data to a curve is not a viable differential equation product. That's called curve fitting, and it doesn't explain something. By the way, it may be very useful. It may satisfy your client's need immensely, and your client doesn't care about a differential equation. But if you really want to understand something, you need to understand how it's changing rather than just what it is. Okay. So I have written a number of articles, and they're all available at our website. This is browsing your way to better teaching. This is advice for teachers on how to browse and find out all kinds of resources that you want. Okay. So examples of browsing, you're having a conversation with a teacher and he tells you about how cricket scores are changing and you go, yeah, they really are. Did the field change? What happened? In the United States, it's baseball, statistics on baseball. You go to a conference, you hear a talk, you get an idea. You invite somebody to your campus, they give a talk and you're listening, but all of a sudden something happens in your mind and you go, I never thought about that. Then you drift off, you don't pay attention and you start scribbling, and before you know it, but you have your lesson for the next day's class. You talk to colleagues about your interests. You look at textbooks. You go to the back of the textbook, and all those exercises that are starred because they're too hard, you take one and you make an activity for it. You look at journals, old and new. You go on Google, my goodness. You go to books, online courses. You can go to Simio. You can go to the newspaper. When I used to teach statistics, elections and polling was very important. You know, how did they take a poll? 1,500 people in the United States can determine whether $1 million television show will be canceled. You know, kids find that amazing. You know, that many people? Yeah. Society web pages, blogs, COMAP is another source. YouTube videos. Everybody has their own teaching videos, con videos, other kinds. Your student assistant has a passion, says, you know, I've always wondered about this. So you get them involved. You go walking through the campus and you all of a sudden notice that the leaves are falling more this year. Why is that? You know, and how many leaves are left and so forth. So work modeling into your classes whenever you can. Don't try to do too much. Just try one. And don't hesitate. I always tell people that after you introduce a model, my colleagues will say, well, what do you do after you introduce a model? And you get them to understand what it is. What's the best thing to do? And I tell them as a teacher, you should leave the room. You should walk out of the room. Because if you stay, you will talk like I talk, and I talk, and I talk. If you leave the room, they have to talk to each other. They got no one else to talk to, and they will begin to, and if you come back and you go, so what's up? They will begin to share with you. Here's an example, and this is one of the last slides I have, and I recommend this to you highly. I would put my students as a consultant. I would put them as a junior consultant, and they would have a project. And the project I had was a calculus project. You could take any modeling activity. For example, you want to grow berries on a bush and you have an acre of land or a hectare of land, and you want to know how many bushes should you plant. Well, you could put a bush every 6 inches. Well, then they would never, ever have any fruit because they're too crowded. Or you could put one bush in a hectare, which is stupid. So the question is, what's the density of bushes to get an optimal yield? And they have to know about fertilizers, density, yields, and everything. But if you look at this article, I put my class as a bunch of consultants. I give them a piece of paper. I walk out of the room, and then I come back acting as the client. I'm first of all Brian Winkle, the teacher, and when I walk out of the room, and then I come back and I put on my theater hat and I say to them, can you help me with a problem? And at first they're very confused because that's never happened to them before. And then after I answer all their questions as a client, I walk back out of the room and I come back as Brian Winkle, the teacher, and I go, oh, I'm so sorry. I was supposed to meet a client for class and I couldn't hook up with him. He didn't show up. And they always look at me and go, oh, he was here all right. And then they start asking me, Brian Winkle, the professor, questions. And I go, I have no idea. I wasn't here when the client was here. And then they realize the theater. And I ask for them to give me a report. And this is most important. They have to give me 2 reports. They have to give me a technical report for the firm. So in case we get theory, or in case we get a problem like this, we can appeal to their analysis. And they have to give me a report to give to the client, to give to the person who's on the shop floor, who doesn't know about mathematics, who doesn't know about even Excel, but says, this is what you do. You put this shop here, you do this here. So this is a very powerful technique. And I have used it on the first day of class when the students expect you to go over all of the materials, you know, the syllabus. I just walk in as the client and they're just like, what just happened? You know, and all of a sudden they wake up and they're excited. And then this report is due a week later. I've also worked with English teachers in learning how to write for audience. So I am pretty much done with my talk, and you have more to go to your conference. Are there any questions or suggestions or ideas you want to raise? If you raise your hand, I'll be glad to answer them. You can see 2 of me because I'm on 2 computers. That's not. Yes, Sudeep.
Hello, sir. Good morning, sir.
Good. Hello.
Okay, my question is a little bit non-related to this subject. My question is related to your career choice and like that, because I am interested in pure mathematics, and you told your story that you did your PhD in pure math in algebra. Am I not right?
Yes,
Not wrong.
yes.
Okay, so I am asking the motivation or what inspire me. It is some rational thinking, or what inspire you to shift your career towards applied math?
By the way, when I published a journal on cryptology, that's largely pure math. A lot of it is number theory, as you know, in public key, and a lot of it is algebra. So I didn't abandon it entirely, but I found more joy in teaching applied math, modeling differential equations, operations research, than I did in teaching pure math. It's just a matter of my interest. And by the way, even inside pure math, supposing you were like I was studying quotient rings in Noetherian ring, associative ring theory, I could have switched over to group theory and finite groups, and that would have been a major shift, but it would have been still inside pure mathematics. And sometimes you may shift because you go to work for a company and they want you to work on this project and you don't know anything about it. You go to work for an insurance company and you have a major in statistics, and all of a sudden you're setting a premium policy on a dental health insurance policy for a company for 20,000 people. Now you're a statistician who's doing actuarial science, and that's not what you thought you'd be doing. The same with teaching. You go to a small college and they say, I need someone to teach algebra. And you go, no, I'm in topology. I don't know much about it. That's all right. Here's the book. If you can get a PhD in topology, you can learn how to teach algebra, and so your interests are forced on you in terms of someone says, try this. So there was no one thing. And like I said, I had been living in graduate school in a very narrow world of pure math, and I loved it. And then when I got out, I went to the science library in my small college, and I began to read about articles in ecology and in chemistry and in physics. And I was not a very good physics student. They would never let me use the equipment because I would always break it. So I was more theoretical even in that. So you can change, but you don't have to force it. It will happen if it's going to happen. And sometimes you resist, and that's fine. And other times it's like, yeah, I'll give this a try, and a whole new world. I never thought I would be editing journals. I almost majored in English, but I never thought of it as an editor. Sagar, you have a question? Hello. Oop, we lost. No. Well.
Hello, Sagar, go on with your question. Sumedha?
Yes.
Sagar, you may write your question in the chat box also.
Oh.
I think, sir, he disconnected.
So may I ask one question?
Sure.
Sir, I have solved many mathematical models using different techniques, mathematical techniques, but I have never worked to form a model, mathematical model. Now I want to start something in this area. I want to model mathematical. I want to formulate a mathematical model. Sir, how should I start?
Well, the first thing you start is you identify what you think the variables of interest. So some of the variables could be friction, and you go, that has nothing to do with it, so forget that. And the other one has to do with the time of day, because you're talking solar energy. You just write down all of the things that are related, and what are the interaction possibilities. So you're writing this down in a sentence, or just scratching ideas. Then you're identifying the variables, and then you're identifying the possible interactions. And then you have to say, my natural gravitation is that nothing stays constant. If it stays constant, it's not worth modeling. Okay. So everything that I tend to model has change in it. And when we have change, then we have the rate at which something is changing. And what causes it to change? Well, the accessibility to food. I have a bird feeder outside, and every day I fill it up, and every day they eat it all, everything. But it is winter here, and so I feel good about feeding them. I don't feel good about feeding the squirrels that are eating it. So if I was building a model, I should build in squirrel eating as well as bird eating, right? So you try to do that, and then you try to get the interactions. You also try to get some data if you can. You also look at how other people build models. And if you look inside Symio, almost every one of them has material on how the students built the model. And almost always you fail. In other words, the first thing you do is you pose a model, and then immediately you pound it with questions. You ask of it, what about the trivial case? Does it work? So for example, if when you build a model for the amount of sugar in some process, and when you start by saying, well, let's have no wheat in the bowl, okay? And when you have 0 wheat in the bowl, you keep getting sugar. Well, then there's something wrong with that model, So you ask critical questions all the time, and you want to encourage your students to do that. Identify the variables. First of all, find something that's interesting to you. And it could be something as simple as a falling column of water. I mean, it could be the amount of leaves that build up, the amount of whatever you're watching, the rate at which snow forms on the edge of a table. You don't know what snow is very much, but it tends not to be just rectangular, it tends to be round. So you might want to know what happens at the edge, okay? And if the mathematics gets too deep, or it becomes a partial differential equations and you're not comfortable, you have to decide, do I go on and learn more, or do I simplify and reduce the reality, or do I just quit and say, I'll try something else, okay? So there are lots of books on modeling, and they're online, and we have 20 plus free online textbooks we post for you to just download, all on differential equation modeling. So you can look those up. I think I'm going.
Thank you, sir. I will definitely formulate and get back to you.
And it's a lot of fun also when you try it, and it's even more fun when you run down the hall on your colleague's whiteboard and say, look at this, and they go, oh, well, I guess we could do this. And what happens if we apply heat? Now they will get overexcited and make it much more complicated, but then you say, let's just keep it simple at first. Yes. But okay.
Right. Thank you, sir.
Thank you.
I would like to take a moment to express our sincere appreciation to our esteemed speaker, Winkle sir, for gracing us with his presence and sharing his knowledge and expertise with us. So the way you explained intraocular gas model, like how does the gas get out and replaced by the body fluids, and then the LSD drug model. And I think we really got engaged when you told that this comes out in the form of a differential equation. So we appreciate your willingness to take time out of your busy schedule to come and share your insights with us. Thanks a lot, sir.
Thank you. I only wish I could visit you in person. Okay. So, all right. Well, thank you.
We would love to in physical mode.
Yeah, I have so many friends throughout the country of India, and I almost applied for a Fulbright to go to Bhutan. And then I know I would have come through India and visited my friends, but that never happened. And so anyway, I thank you all very much. And you can always get in touch with me at my name is, I will just put my email in the
chat box.
Yeah.
Now, I would like to request Mansavi to please present memento and certificate to Professor Winkle as a token of gratitude and remembrance on behalf of JCRC Foundation.
Oh my.
So please accept this as a token of remembrance and gratitude from all of us, sir.
Well, thank you very much. I'll have to share this with my grandson who is in high school and tell him that I get certificates as well. I thank you all, and I thank you, Dr. Punia, for inviting me. And it was good to see you and hear and talk with you in preparation. And I wish you well in the rest of the conference. And right now, I'm going to go to sleep so I can get up early tomorrow morning, my time, and visit my doctor.
Thank you, sir. Thank you so much.
Okay. Bye now.
Thank you so much, sir. Bye.
Thank you, sir.
Thank you, sir.
Bye.
Now, I would request all the participants to rejoin the conference at 11 a.m.